In this segment, I want to start getting into antenna design. Now, if this is the first segment that you actually are paying any attention to, I'd highly recommend that you track back a couple of episodes and take a look at the other previous segments I've done about radio connectors and coax. That's very important. Do not just jump straight face first into this. You'll probably fuck something up, and you'll most likely damage something, or just things won't work. The bottom line is you have to have the appropriate coax and appropriate connectors and a device that has those connectors and such. So, past couple of episodes, I've been focusing on how to connect an antenna to your device, how to mod your device, how to get the proper coax, how to crimp stuff. That's over and done with. Let's learn how to make some antennas. But before we can do that, we have to understand some principles of what a radio wave is. So I've got a couple of slides in a presentation here, so let's go ahead to that and I'll try to explain some of the fundamentals. You have to understand that frequency is a measurement of oscillations of a sine wave for every second. Now, a sine wave is an electrical wave that'll actually repeat up and down from a positive to a negative so many times per second. That is what frequency is. How many oscillations per second? Now, you have to understand wavelength. And the wavelength is the distance between two common or similar points on that waveform itself. This little symbol on screen is our friend lambda. And lambda is the Greek character in math for wavelength. Whenever you see this character, it is going to symbolize the equivalent understanding of what your wavelength is. So this means wavelength. Now, to calculate the wavelength, we need to know c, which is the velocity of light, and f, frequency. So, the letter c is going to take place for the velocity of the speed of light, and lowercase f is going to take place for our frequency. So, because we're going to be working a lot in 2.4 gigahertz, we know that the frequency is going to be 2.4 gigahertz, and we know that the speed of light is 29,979,245,800 centimeters per second. So lambda, or wavelength, is equal to c divided by f. So your wavelength is equal to 29,979,245,800 divided by 2,000,000,004,000,000. And when we plug these values in for Wi-Fi, the wavelength comes out to about 12.49 centimeters or 4.9 inch. So there we go. Now we understand what the wavelength is. The wavelength is the actual physical distance between two common points on a sine wave, or on a radio wave. And the reason we need to know this is because our antennas need to be specifically tuned to that wavelength. The reason being is an antenna is essentially a net for radio. So when you have an antenna, when that wavelength changes, when that physical size of that antenna changes, you're also changing in what it actually absorbs on that frequency. So this is how you tune an antenna specifically for a frequency. So, we know what wavelength is, we know what frequency is, we know the basic concept of what an antenna does, but really, do you understand what an antenna really does? Let's say that this balloon, for a lack of a better example, because I don't feel like spending 3 hours to go and do a computer-generated simulation on a presentation that should only take 15 seconds. Let's say that this little red balloon is a visual representation of your radio field, or your estimated radiated pattern. In the very center of this, right around here, would be your transmitter. What your antenna is basically doing is it's going to manipulate this field of energy so you either have more or less gain. So, right now we have a perfect sphere. Now in radio this will never happen, this is just for visual sake here. Now, we have an antenna, and let's say today we're going to make some dipoles. And what it's going to do is, it's going to take this ball of energy, this estimated radiated pattern, and it's going to squeeze it. And if you notice, when you squeeze it, the sides squeeze out. squeeze out of the side. Same thing, so if we were to go this way, it'd squeeze up. So what the antenna is going to do is it's going to sacrifice height for distance. So, other types of antennas are like beam or directional antennas. What it'll do is it'll squeeze the back end. So it'll do that. You notice how you got a nice frontal lobe? Each one of these bubbles are called lobes. In some antennas, what they'll do is they'll squeeze the middle. So by squeezing the middle, the sides stick out. So yeah, you're going to be losing height or you're going to be losing the direction from one end. But what you're doing is, an antenna is effectively manipulating that field of energy like this balloon is being manipulated by me. So some of the antennas that we'll be eventually designing will actually take the back end of it and do that. But if you design your antenna wrong, well, that's what's going to happen. So, it seems like it's really complicated, but this is just another step of the process. What your antenna is actually doing is, it's taking that field of radiated energy, of radio wave, and it's taking that aura, and it's actually going to mold it and manipulate it into what you need. You can't add energy, you can remove it, but that's kind of defeats the purpose of this. See, people actually think that just because you add an antenna to something means you're going to get better range. Or some other people think that just because you increase your power output means you're going to broadcast further. To be all honest, a good antenna is usually more important than really strong power output, because if your antenna isn't pushing out that signal where you want it, or if it's not tuned properly, it's not going to work. So, let's go to the table side, and I'll get to building our first antenna called a dipole. Now, a dipole is an antenna like a pole. You know, you have a positive and a negative. Dipole means you just have two sides. And in a previous segment, when I was doing Introduction to Radio and Radio Scanners, I explained dipoles and beam antennas and things of the such, so you might want to go back a bunch of episodes and check that out. So let's go to the table side, and let's start putting stuff together. Before we begin, I want to analyze a couple of commonly found dipole antennas that we have in our 2.4 gigahertz products. The first thing I want to show is, we all seen these little default antennas that come with your router. These are called rubber duck antennas, oftentimes because the rubber that they're made out of are often used in the bath time rubber duckies that you find in pedophile rape kits. It's got a standard reverse polarity SMA connector, and inside of this is a typical dipole. Now, we all know from experience that these aren't the best antennas to deal with, but do you really know why? And I've got a couple more antennas that are similar to this, and we'll actually explore that fact before we get into anything. Now, we've also got the antenna that I removed from the USB Wi-Fi card from a couple of segments ago. For the sake of learning and understanding, I decided to put the antenna on the sacrifice block, and I cannibalized it for you guys. This is the antenna. It's just a circuit board. Nothing more, nothing less. Not very complicated. And the third product that I decided to go and pillage and destroy and make look fugly as all hell for you guys is my 2.4 gigahertz security camera. If you've noticed that this antenna is nothing more than, quite literally, the shield has been stripped away from the signal conductor, and then a tube has been soldered onto the shield end on exact wavelength, or I should say size. So I take my compass, and using it kind of like a caliper, I've measured this, and it turns out to be 2.5 centimeters on both sides. So we got 2.5 centimeters here and 2.5 centimeters there. And doing some math on the wavelength, 2.5 centimeters should come out to about 1/4 wavelength on each side. So this side is quarter wavelength, and this side is quarter wavelength of 2.4 gigahertz. And if you expand them both together, that means this is a half wave dipole, because we have 1/4 on each end. Now, you might be asking yourself, well, if that's the case, why can't I make a 2-wave dipole? And the reason being is because you have to remember, when you change the length of the wire, you're changing the offset frequency. You're changing the frequency that it can receive. So if this was excessively long, like if it came out to here, well, not only would it be really bulky and, you know, disgusting looking, but it would also pick up a different frequency. So you have to make sure that your antenna is properly tuned to the frequency that you're picking up. So if we were to, on average, a full wavelength of 2.4 gigahertz is almost 5 inches. So if you have one wavelength on each side, that'd be a full wavelength dipole, but that could also change. You could also be picking up spurious frequencies across other bands. So this is usually why you keep things as specific to the frequency as possible. And this is also why you can't just get like a 30-foot long piece of wire, attach it to your Wi-Fi card, and get all of the signals in the neighborhood. Okay. This little bugger. When I measure this, it came out to be 2.5 centimeters as well, which means that little circuit board, yep, 2.5 centimeters. This little circuit board has 2.5 centimeters on it on each side, and that creates a half-wave dipole. Yay. Why are we using half-wave? Why can't we make something better? But a lot of times half-wave works just fine. Now, if you wanted to make one, the first thing you're going to need to do is, of course, as always, make sure you have the appropriate coax. Reverse polarity SMA going into, I forget what kind of coax. I sacrificed this off of a really crappy antenna. Now, we're going to copy the design that these guys are using. So we're going to need some kind of tubing or some kind of pipe. And this is going to actually fit down the center of this. And then we're going to solder a length of wire out of the top. Now, I got that tube from an old antenna, an old TV antenna. Oh, go away, balloon. Remember the old rabbit ear antennas for TV, for broadcast TV? Well, of course, you can't use this antenna as is. So what I did was I extended it, and I just cut a segment out. And that's where this tube came from. This literally came from a leg of an old TV antenna. Now, you might actually have something else laying around the house. Like you can actually go to the hardware store and you can buy a brass tube. This tube actually has the exact outer diameter and inner diameter, so you can actually feed LMR 195 coax down this hole. So this would be good for a really nice, sturdy antenna. So we've got the antenna, and I've marked 2.5 centimeters. As for the actual wire itself, any wire, here's some household power cable that I pulled out of the garbage. I pulled the sheathing off of it just so I can solder it. You can use an old coat hanger. Here's a small length of coat hanger. Just something metal, something conductive, and something you can solder to. So, I'm going to use a very little saw. Got a little miter saw here. I got it from the dollar store for $1 with a couple of extra blades. And I've marked 2.5 centimeters, and I'm going to go ahead and I'm going to go and saw this off to the proper length. It took a little bit of effort, not really, but for the sake of just bitching and complaining. Anyway, here we go, got our marker. I'm going to go and mark up 2.5 centimeters. 2.5 centimeters. Okay. And then we're going to take some wire cutters. I've already pre-tinned this wire just for the time constraints. We're going to cut this wire. Now, whenever you're making something for 2.4 gigahertz, try to stay as spot on to your measurements as possible. So, having a hand file around and actually filing down things down to the closest millimeter is a good idea. Personally, I tried to be less than half a millimeter off, but if you are, it's really not going to kill you. It'll probably could kill your Wi-Fi card, but that's besides the point. Okay, so we got the tube end, and we've got the little nubbin end. So, let's go ahead and get this on the coax. Got a little razor blade here, and I'm just going to pull off this outer insulator to reveal the shield, trying very carefully not to actually pierce the shield, or even the center conductor, and then just, peel the shield. Well, actually, first thing you got to do, sorry, I always forget to do this. Go ahead and put your collar on first,